All right, let's jump right into this explainer. Have you ever wondered how the mathematical shield protecting modern decentralized money is actually, literally, tied to the secret code-breaking huts of World War II? Well, that's exactly what we're going to unpack today. We're bridging the gap between Satoshi Nakamoto's revolutionary consensus model and the absolute genius of a World War II codebreaker named David Rees. To guide us through this, here's our quick roadmap. We'll start with trust without central authority, look at the double spend threat, and then really dig into the math with the binomial random walk and the Poisson probability shield. Finally, we'll introduce David Rees and Enigma to see the ultimate legacy of this probability math.
Okay, Section 1. Trust without central authority. Let's look at how we actually establish trust without a referee. Think about it for a second. How can we possibly trust a financial system with no boss, no bank, and absolutely no central server? This right here is the fundamental problem the 2008 Bitcoin white paper set out to solve. Imagine a network of completely anonymous, trustless nodes. How do you get every single one of them to agree on the exact same sequence of events? In a traditional setup, you just have a central authority, right? A bank to maintain the ledger. But in a permissionless system, anyone can join, which means anyone could potentially lie.
So, instead of a central bank stamping the transaction as valid, imagine a massive town hall where everyone in the room holds a matching copy of the ledger. A transaction is only considered valid if the majority mathematically votes to include it. And how do they vote? Through proof of work. Participants prove their honesty by burning verifiable computational power. They're racing to solve these intense mathematical puzzles, and the rule is simple. The longest chain, the one with the most cumulative proof of work, is the accepted truth.
Which brings us to Section 2, the double spend threat. Because this town hall model, it introduces a very specific vulnerability. Nakamoto saw this coming. It's called the double spend attack. Picture this. You're a merchant, and you just sold a car for Bitcoin. The attacker sends a transaction to the network paying you. You see it pop up, so you hand over the keys. But wait. Meanwhile, the attacker is secretly using their own mining power to build an alternate, hidden version of the blockchain. In that secret chain, they alter the transaction to send those exact same coins right back to themselves. If they can build their hidden chain faster than the honest network builds the public one, they unleash it. Because it's longer, the network adopts it, and poof, your payment completely vanishes.
Okay, Section 3. The binomial random walk. Let's see how the network actually survives this attack by looking at the math in Section 11 of the white paper.
Nakamoto modeled this whole race between honest nodes and an attacker as a binomial random walk. You can picture it like a heavily rigged coin flip race, or maybe a massive tug of war. The whole process moves along a series of states connected in a line. When the honest network finds a block, that's a success. They take one step forward and increase their lead. But a failure? That means the attacker found a block, pulling the honest team one step back.
Nakamoto famously wrote, "The race between the honest chain and an attacker chain can be characterized as a binomial random walk." And this is a brilliant insight. He modeled the security of a global financial network as a stochastic process of +1 and -1 steps. Every single time a block is found, it's an independent Bernoulli trial. As long as honest nodes control the majority of the computing power, their probability of finding the next block, let's call it P, is always going to be greater than the attacker's probability, Q.
He then compared the probability of an attacker catching up to a classic math concept, the gambler's ruin. Imagine playing against a casino with literally unlimited funds. If a gambler starts at a deficit and keeps playing to try and break even, the exponential odds will absolutely crush them, because the house has the statistical edge. It's the exact same dynamic here. Because the honest network has the statistical edge, if the attacker falls behind early, their chance of catching up from that deficit plummets exponentially.
Moving right along to Section 4, the Poisson probability shield. How do you, as a recipient, actually use this math to protect yourself?
You use what we can call a Poisson shield. Remember our merchant selling the car? They don't just hand over the keys the second they see the transaction. They wait. They wait for the transaction to be packed into a block, and then they wait for a specific number of subsequent blocks, denoted as Z confirmations, to be built on top of it. Now, the merchant has no idea what the attacker's doing in secret, but they can calculate the attacker's potential progress using a Poisson distribution. Why Poisson? Well, when you have billions of hashes, a massive number of trials, but a tiny chance of success for any single hash, a Poisson distribution is the perfect way to approximate the binomial reality of the attacker's progress.
As you can see on this graph from researchers Ozisic and Levine, the attacker's mining power is plotted on the bottom against their probability of success. Those different colored lines, Those represent different values of z, the number of blocks you wait. It's visually striking. As the number of confirmations, z, goes up, those curves just completely flatten out. It mathematically proves that as long as the attacker has less than 50% of the network power, their odds of success crash toward absolute zero the longer you hold off.
So here's the absolutely crucial takeaway. By waiting for just a handful of blocks, say 6 of them, an attacker with a massive amount of computing power has less than a 0.1% chance of rewriting the ledger. Think about that. The protocol isn't enforcing digital scarcity with bank vaults or armed guards. It's enforcing it through the uncompromising, ironclad laws of exponential probability decay.
All right, Section 5, David Rees and Enigma. Time to uncover the historical foundations because this specific flavor of probabilistic thinking definitely wasn't born with Bitcoin.
The roots of using probability this way actually trace back to a brilliant Welsh mathematician named David Rees. Born in 1918, he was studying at Cambridge when World War II broke out, and he was rapidly recruited into the highly secret code-breaking huts at Bletchley Park. Post-war, he became an absolute titan in pure mathematics, doing groundbreaking work in commutative algebra and eventually snagging the prestigious Polya Prize in 1993.
But it's his work at Bletchley Park in May of 1940 that really ties into our story. Rees was instrumental in cracking the red Enigma cipher used by the Luftwaffe. And he didn't do it by brute forcing the machine. He used probability. He leveraged something known as Hurrivel's tip. See, the Enigma machine itself was supposed to be completely random, but the humans operating it? Not so much. A tired, lazy German operator setting up the machine first thing in the morning might just leave the rotors clustered near where they finished the night before. Rees mathematically exploited that laziness. He proved by predicting probabilities over human biases could break a system that was theoretically impenetrable. And that brings us to our final section, the legacy of probability. Let's finally merge these two worlds together.
The legacy connecting these two eras is honestly profound. At Bletchley Park, David Rees used reductionist logic and probability to exploit human bias and shatter the Enigma codes. Fast forward to 2008, and Satoshi Nakamoto employs the exact same type of stochastic modeling, binomial walks, Poisson distributions, to actually defend a network. Bitcoin's proof of work essentially replaces our reliance on potentially biased human institutions with a total reliance on the uncompromising laws of math. It creates a system resistant to human corruption precisely because it's anchored to the mathematical certainty of the gambler's ruin.
Which leaves us with a truly fascinating question to ponder. We tend to view blockchains and decentralized consensus as this hyper-modern, cutting-edge tech. But when you strip away the massive server farms and the cryptography, isn't their true foundation just the brilliant application of World War II probability math? The mathematical shield protecting trillions of dollars in digital value right now is woven from the exact same conceptual fabric that helped turn the tide of the Second World War. It kind of makes you look at the math behind your money in a completely new light, doesn't it?